Hello all, welcome to this channel cfdbaba. Here we simulate CFD cases using ANSYS Workbench Fluent. Today we are going to simulate CFD case of flow through exhaust manifold. To start the workbench, type in Workbench in your search bar and open the Workbench app. Next, we will drag in the Fluid Flow Fluent tab. We will start by importing the geometry. Right-click, import the geometry and select the geometry file. Right-click again and let's edit the geometry in space claim this time. As you can see, the imported geometry is not a fluid domain. It is a solid domain which is hollow. For CFD simulation, we need to create a fluid domain out of the solid model. To do that, first I have to create a single body. For that, I will use the Combine tool from Design tab. Select the lower body and then select the upper body after clicking on the green icon. This will merge both the bodies and you can see that as the last part. We will delete all the other parts which are useless now. We have our single model of the geometry. Now we will extract the fluid volume by going in the Prepare tab. Now we will select the edges which confine the geometry of our fluid domain. We will select 4 inlet edges and 1 outlet edge at the top. Once you select all the edges, click on the green complete button. This will extract the fluid volume. Now for a CFD simulation, we just need the fluid volume. We can suppress the solid geometry. Right click and select Suppress for Physics. If you hide it, you can see the extracted fluid volume. We will use this for our CFD simulation. There are 4 inlets at the bottom and 1 outlet at the top. Now the next step is meshing of the geometry. So we can close space claim. Right click on mesh and click on edit. This will open the ANSYS mesher. Let's first create a default mesh and see what the software gives us. Right click on mesh, click on generate. You can see that the software has created a default mesh. If we zoom in near the inlet, you can see that it has created some unnecessary fineness in the mesh. We can fix this. Go to the sizing and select yes for adaptive sizing. Let's generate the mesh again. Clear the data and generate the mesh. You can now see that the fine elements at the inlet have now vanished, but the mesh is too coarse right now. So we need to increase the fineness of the mesh. Let's check the quality of the mesh. We can see the skewness is 0.99 as the maximum value. It is very high. The required skewness is recommended at 0.8. Let's try to reduce the maximum skewness value. To do that, we will reduce the element size. Let's take element size of 4 mm. I have selected this size because you can see that the length of the arc is 23.562 mm. So, if I calculate the total length of the circle, you have to multiply this value by 4. So if I select all the edges, you can see the total length is 94 mm. So if we create element size of 4 mm, it will divide 94 mm by 4, which will give us almost 23 cells. So let's generate the mesh again. You can see that a fine mesh has been generated, which is quite uniform. And if you check the skewness value, it is around 0.85. So skewness below 0.9 is acceptable, but good skewness is always below 0.8. Target the skewness to 0.8 and generate the mesh again. If we see the skewness is same 0.85, so let's leave it at this. Good mesh gives you good convergence in results, so your simulation gets calculated faster. Now the next step is to name the boundaries of our geometry. Select the face selection filter. The shorter length pipes will carry air which is at relatively higher temperature. The longer pipes will carry air which is at relatively lower temperature. So let's name the boundaries. The outer two inlets will be named inlet 1. Right click, create named selection and name them as inlet 1. Select the inner two faces, press the N button and name them as inlet 2. Select the top face, press the N button and name it as outlet. Now we need to select the walls. To select the walls, press Ctrl A, deselect all the patches of inlet and outlet, press N button and name it as walls. Now we can see all the boundaries. Inlet 1, which will have relatively higher temperature. Then we have inlet 2, which will have relatively lower temperature. We have one outlet and we have the walls. We need the walls to apply the convection boundary condition. Select the volume and make sure it is of the type fluid. Right click on mesh and click on update. This will successfully translate the mesh to Fluent. Now you can close the meshing module. Next we'll set up the case. Right click on setup and click on edit. It will open ANSYS Fluent. Now select double precision and use solver processes as 4. These are the number of cores. I have 4 cores. Click on start. The model has been successfully imported. Now let's set up the case one by one. In the General tab, we will use the steady state case with pressure based solver. Click on check and check the minimum volume cell. It should be a positive value. If it is a negative value, you need to change your mesh. Go to models, click on energy and turn it on. For this case, we will use the viscous K omega SST model. We will leave all the values as default values. Click on OK. Next, we make sure that the material selected is air. Double click on cell zone and select the fluid volume. Make sure it is of the type fluid and air is assigned to it. You can check that by clicking on the edit. Close this. Next we'll set up the boundary conditions. For inlet, we will set up velocity inlet boundary condition. Click on inlet 1, select velocity inlet, click on edit. We'll use velocity of 0.3 meters per second. We will use temperature of 900 Kelvin. Click on apply. Click on close. For inlet 2, we will use the same velocity of 0.3 meters per second. And in the thermal tab, we will use temperature of 850 kelvins. Click on apply, click on close. For outlet, make sure that the boundary type is pressure outlet. For the walls, the boundary type is wall, and now we will set up convection heat transfer boundary condition. Go to the thermal tab and select convection. Enter heat transfer coefficient of 20. Let's keep free stream temperature at 450 Kelvin. Click on apply, click on close. Next, make sure that all the methods selected are second order. It will give us more accurate results. Double-click on initialization and initialize the case with hybrid initialization. Now we'll run the calculation. Double-click on Run Calculation and enter the number of iterations as 100. Click on Calculate. This will start calculation of the solution. You can see that the residual graph is being printed on the screen. Residual values are nothing but the difference between the calculated values and the actual values. We want this difference to be as less as possible. That's why we want the residual values to go down. That will be seen when the graph slope goes down and reaches the value of 1e-4 on the y-axis. At that time, we can say that our solution has converged because the convergence criteria of 1e-4 is set as default in ANSYS Fluent. Let's wait for the solution to complete. After the solution is completed, click on OK. You can see that all the residuals have reached the order of e-4. Now let's check the results. The most important thing we want to see is the velocity and temperature of air at the outlet. We'll also see the pressure. Double-click on Reports, select Surface Integrals, click on Area Weighted Average and select Temperature. We want to view temperature on the patches inlet 1, 2 and outlet. You can see the values printed in the console. We can also check the velocity values. You can see that the velocity has increased at the outlet. And we can check the pressure values to calculate the pressure difference inside the manifold. It is almost 1.12 Pascal. This is how we can calculate the quantities inside ANSYS Fluent. Now we'll do some post-processing of the results. Close ANSYS Fluent and right-click on the results. Click on Edit. This will open CFD Post, which is a post-processing software inbuilt inside ANSYS. After the results are loaded inside CFD Post, we will start the post-processing. We can view contours and streamlines here. Double-click on wireframe and increase the line width. You can see that the line width gets increased. Let's keep it at 1. Let's change the edge angle. If we increase the edge angle, you can see that we see fewer elements of the mesh. And if we reduce the edge angle, you can see that we can see the whole mesh. Let's keep the edge angle at default value of 30. We just need to see the boundaries of inlet and outlet. Let's plot a contour. Click on the contour button, click on OK. We want to plot the contour of pressure. Select the location as walls. Click on Apply. You can see that if we increase the number of contours, you will get a more smoother image of the contours. You can see that there is high pressure at the inlet and low pressure at the outlet, which is required for the flow to happen. We can switch off the lighting from the Render tab to see the results more clearly. We can select the location as all the patches and click on Apply to see pressure on inlet and outlet faces as well. Now we'll plot the velocity. Click on Apply. Here you can see that the velocity has increased at the outlet. At the inlet we have value of 0.3 and at the outlet we have value of 1.3 meters per second. Next we'll view the temperature. Click on temperature, click on Apply. You can see that the temperature at the inlet is high, but as the air flows through the manifold, the temperature is decreasing. We have already viewed the value of temperature at the outlet. Now we want to see inside the fluid domain. For that, we will plot streamlines. Click on the Streamlines button, click on OK. Click on Start From and select Inlet 1, Inlet 2 and Outlet by pressing the Control button. The walls have been selected. Deselect them and select Outlet. Click on OK. Select Forward and Backward, click on Apply. You can see the streamlines. Increase the number of points to view more streamlines. You can now see inside the fluid domain. You can see the velocity increasing at the outlet as the two pipes bringing the airflow converged at the outlet. Now we will change the color to variable and we can plot the temperature. Click on temperature, click on Apply. You can see that the hot air is coming in through the inlet and as it flows through the domain, it is getting cooled as it reaches the outlet. We can even view the particle animation inside the fluid domain. To do that, click on the Animation button option. Select Streamline 1. Reduce the speed of the animation and click on Play button. You can view how the air particles will flow inside the fluid domain. You can see for the shorter pipe length, the particles are reaching outlet first compared to the particles coming in through the longer pipe length. We can even save the animation by clicking on Save Movie. Let's click on Close. This is how we can simulate flow of air inside the exhaust manifold. If you have liked this video, don't forget to hit the like button and click on subscribe for more new CFD videos. We will meet again in a new video with a new simulation. Goodbye till then.